Hello, everyone. My name is Enriqueta, and I'm going to be guiding this webinar today. And we're going to talk about exploring machine learning in research as a first guide for machine learning analysis. I would like to talk a little about my background. I'm currently a PhD student in Aalto University in Finland, and my main focus of study is material sciences. However, my background is in particle physics, and I've mainly do data analysis, and before here I did particle physics, so I was used to very large data sets and a lot of data analysis and modeling. So this is how I first was introduced to machine learning, and I really like it, so I hope this can be useful for everyone. So first, we're just going to go through how the presentation is going to look. We have the handbook that I'm going to talk a little bit about. Then I want to set like a starting point for everyone of the main understanding of machine learning basics. Then we can go into the different algorithms and how they differ, how they're used. And finally, in the last section, I would try to invite anyone that is interested in applying machine learning to their research or data to be part of some discussion where we would talk about the interpretation and evaluation of these results effectively and what things we have to take into account for this. But this would be more like an open discussion in case anyone has specific questions. So first, let's go into the handbook. The handbook is the main reason why I'm doing this presentation. A year ago, I was told that I was going to be a data agent in our university, and that if I was in the mood of doing any kind of project, it would be very much welcome. Since my background recently has been more machine learning and helping other researchers to incorporate this kind of analysis into their research, I thought that it could be very beneficial for both parts, the machine learning experts and the field experts in other fields, to have common understanding of what machine learning is, what it needs to be implemented, and what kind of results we can expect from it. Often it's the problem that we hear that machine learning is emerging everywhere, but we know little about what exactly it is, and there's maybe even a little bit of a lure to it's kind of magic thing that you just put into your data and it gives you nice results that seem very promising, especially if we want to talk about things like large language models such as ChatGPT, where it seems like we can just have conversations with our computer and it just gives us very good results of what we want to do, if it's like writing down an essay or just doing a very fast, quick analysis. So for this reason, I wanted to work with something that would be very easily accessible to everyone. You don't have to be from a math background or a computer science background. I want to introduce machine learning with no math. Of course, this is a little bit optimistic because even though I will try my best to avoid mathematical notations, math will be there in some shape or another. I don't know if some of you have been familiar with books like Relativity for Babies, where math is there, but babies don't care about this notation. They mainly have different concepts that are described with shapes and forms and sometimes even texture, just to explain very hard concepts that relativity might have, which is kind of what I'm aiming for here. Obviously not aimed at babies, but hopefully it'll just help invite everyone from any kind of background to try to use these tools. For the same reason, I will not present any kind of code. So if anyone is thinking about implementing these kind of algorithms to the data or research they have, they will just have a very basic understanding to discuss this with experts that will probably take care of the code and the math. And finally, for the people that are already quite familiar with this, it's good to have a repository of algorithms. Machine learning nowadays is very promising, and because of that, a lot of people work on it. So every day we have new algorithms or new variables of the algorithms we already know that do some specific task easier under specific conditions. So it's very hard to keep track of how far it's going. And even though you might be an expert in some specific kind of machine learning, it's unlikely that you're going to be up to date or well informed about all the possible options that are out there. And it's often the case that in some publications or talking with my coworkers that want to use this machine learning, they usually use very trendy algorithms, but the task at hand might not need such a powerful or such a resource-consuming algorithm. It might be easier to use a different one that might sound less fancy, but it's also cheaper in terms of computational resources, and it's also more easy to interpret because machine learning often becomes a black box where you input data and then you have something out, but it's then hard to keep track of what exactly is going on and why are we getting these results. So I want to introduce the Machine Learning Handbook. This is how it looks right now. It's been an ongoing project for a year. I've decided to start this with different chapters. Each chapter has some introduction to what supervised learning might be, or Bayesian theory, or general introduction of machine learning, and then it will go through each of the algorithms one by one. So the main structure of the content is going to be the introduction to machine learning algorithms. I'll just present quickly and as efficiently as possible what these algorithms are about. And in some cases, it is relevant to go step by step and see how these algorithms are implemented. No code is used, but I would like people to have a general idea of the main steps of what the code is doing and the relevant bits, and especially the parts where human interaction with the algorithm is relevant for interpretation and assessing of what the algorithm is doing. In some cases, this is not possible because it's just not the shape of how the flow of the analysis goes, but in a lot of them, it's nice to see how it's working. At the same time, we're also going to address some troubleshootings and common challenges within these specific algorithms. And finally, and possibly one of the main parts of the handbook, it's going to be the practical application and possibilities. So since machine learning has been around for a while, there's already a very large area where we already have very good results in different aspects of everyday life, but also in research. So we can assess how this has been working so far and which algorithms have been outperforming others and why in specific questions or analysis. But the heart of the manual, as I like to call it, are these red pages that you're going to find after each description of each algorithm. I call it the heart of the manual because the idea is that you don't have to go through the whole manual to get a general overview of what is out there that can possibly help you with your analysis or research or study in general. You can just skip everything else that I've been talking about and just go through the red pages. And the red pages are going to tell you which algorithm we are using. Each chapter has at least 2 algorithms representing it. Then what does it do, like in a very concise, simple way? Then how does it work? Just a very fast way to help people understand what is happening to the data and how it's changing throughout the whole process. What kind of results do we get? Is it an image? Is it a table? Is it a prediction? Is it some kind of probability? And finally, the most common applications. So what are these algorithms being used for right now, and how they been performing so far? Even though I have these red pages in the handbook, I also have these other colors. So red is the heart, but other colors are the lungs, muscles, kidneys, liver, and bones of the manual, and so on and so forth. Because here I want to make sure that everyone is in the same page. So people that are already familiar with these concepts can just ignore it. But if for some reason you don't remember or you're unsure of what I'm referring to in some of the explanations, these boxes with different colors, such as blue or orange, are just reminding the reader of basic, mainly probabilistic and statistical concepts. Oh, sorry. So now we're going to go to the next part of the presentation. And here we're going to just talk a little about the understanding the basics of machine learning. Okay, so machine learning is a field in artificial intelligence where computers learn and improve from experience without explicit programming. It optimizes performance criterion using example data. There are no explicit instructions. It identifies patterns in the data to make predictions or decisions. This approach enables systems to adapt and evolve, enhancing their performance over time. Traditional analytical methods may struggle to extract meaningful patterns from big amounts of information, but machine learning excels in handling such datasets. Researchers can use machine learning to identify trends, correlations, and hidden patterns that may not be apparent through conventional analysis. Machine learning is capable of automating tasks, and it facilitates predictive modeling. So a lot of people might already be quite acquainted with machine learning. They just knew it with a different name, which is statistics. So what is happening nowadays is that with better technology, better computers, we're just getting better and better at performing statistical analysis and withholding the information and saving it for further analysis, and then inputting that into more complex models and more math and more algorithms. And this is why we're calling it machine learning nowadays. However, it can be broken down to just statistics and computer things. So the significance of machine learning has been evolving a lot recently. Let's explore how machine learning can contribute to different aspects of research and studies. The first one would be data analysis and pattern recognition. Here, we're going to take advantage of how good computers are at recognizing patterns in very large data sets. And even though humans are also quite good at that, we do have a very natural limitation, which is memory. We might not remember what we identify as a pattern from the first samples when we're in the 1,000th sample. However, a computer will. And this is one of the main reasons why we start dwelling in this area with machine learning. The second one would be predictive modeling. This is a very powerful tool, I would say, because it gives us the option to put all the knowledge we have as human race since forever and then make predictions out of it. And finally, I would talk about the optimization and decision making, which has to do a little bit with the previous. So if we already have established processes, such as in the industry, we might want to optimize them. And machine learning can prove to be quite efficient in this task. They might enable optimization in different kinds of processes, but it might also help us do decisions that will improve these performances further and explain why and how this is either predicted to work better or why this optimization might enhance efficiency. So now we're going to look into what machine learning is. We've talked about it for a while, but it's a little bit not still certain what exactly it is. So when you work with machine learning, you have a workflow. The breakdown of the typical machine learning process takes many shapes and forms. It varies a lot depending on what kind of data we're looking at, what our targets are, what we want to get from it. But ideally, we want to have data collection and preparation taking into account that we want to use a machine learning algorithm. So ideally speaking, from the start, we will design our study considering this so that we know what kind of information our algorithm will want to have or is best at performance with this, either a table or numbers or some kind of survey. It depends. However, if this is not the case and you already have a data set that it's very good for some reason or very old or very hard to achieve, and you've already done some analysis, but you just want to do it again, but with machine learning to see if anything was still missing from there, it's also possible. Machine learning, it's highly adaptable, and we also have steps such as pre-processing that help data be more catered to specific algorithms or targets that we want. After that, hopefully we've decided on a model and we just have to implement the model and then train it. In this phase, it's probably the moment where experts are most needed because we really do need someone to guide us in the code and what the code is needing and what different resources they're going to be emerging from it that we will need. Finally, we have the evaluation and validation. In this step, it's kind of very important for everyone that is involved, even if you're not part of the coding part, even if you're not part of the machine learning part, to assess the results and check that everything makes sense. Because the thing about machine learning is that it will always give you a result. The result might not be good because the interpretation in the real world might not make sense. But this is where the human input comes in. And this is why machine learning is so powerful, because it's constantly being assessed by experts that tell it it's good or bad and try to improve it. Finally, if this step is sufficient and if you're not super into academics and you want to go a little bit further and not just publish something, you can also deploy your model. In this step, you have to be particularly mindful of the evaluation and validation because machine learning would learn patterns. And if you want to apply it to society things or public things, it will learn patterns that might not be good or perfect. And you don't want to perpetuate these biases that we have within society. So it's always good to be very aware of the possible impact of the deployment of machine learning algorithm and be aware of all the legal and ethical aspects to it. So, as I've been saying, machine learning can be a powerful tool in research. The machine learning algorithms are adept to process large datasets and identify patterns. However, the contextual understanding provided by human experts is indispensable in ensuring the accuracy, relevance, and ethical implications of the outcome. So this is part of the interpretation, and it's key and fundamental aspect of any machine learning analysis. So it's not that you can contact someone to do machine learning for you or the analysis for you, and then you can just trust whatever comes out of the algorithm. So going back a little to the handbook, I just wanted to overview key machine learning algorithms, how I divided them. These divisions are not absolute. I decided to divide them this way. However, the contents of each of these classes might overlap if you consider a different classification criterion. But for now, we're just going to look into supervised learning, which is mainly label data. And here we will find a lot of algorithms that might be familiar to many of you since it's very much statistics. And it's classification and regression, for example. You also have support vector machines, for example, or decision trees. Then we have unsupervised learning. Here, the main difference is that you don't have labels. So you might be looking into data without knowing exactly what it is, but you know there's some differences. And in here, the interpretation from the experts becomes more relevant because you do get some result that doesn't mean anything until you say what it is. Here we have things like many kinds of clustering and image compression. Then we have other techniques, the reinforcement learning and association probability. So here we have algorithms such as neural networks, random forest, gradient boosting, and these are a little bit more complex and might be the product of implementing many previous simpler algorithms into one and make a structure or an architecture out of it that would help us study something specific. As I've been saying, machine learning, it's becoming more and more recurrent in our everyday life and also in many, many aspects of everything. Mainly, I basically ask ChatGPT what these machine learning things are being used. And these are some of the results I got. Turns out that healthcare is actually using quite a bit of machine learning for mainly prediction, disease prediction. Finance fraud, it's also quite good at detecting something that it's normal, that it's not normal in someone's account or expenses. In biology, we have genomic data analysis that mainly benefits from the aspect that machine learning performs very, very well with very large data sets. So genomic data analysis has this kind of data sets, and it so far works very, very well. And finally, we have things like social sciences that use it for sentiment analysis. Here we just give ChatGPT a text and we can tell it to tell us what it sounds like. Is it friendly? Is it angry? Is it informative? Is it in some kind of style from a famous author? So this is becoming more and more relevant in large language models, but it's always improving. But it seems a little bit magical that machine learning is able to do all these things, all these tasks at once, almost as if all the things a human can do, machine learning can do them faster, better. But it comes at a cost, and the cost is from high-performance computing. This refers to the use of advanced computing techniques and systems to solve complex problems, process large volumes of data, and perform computations at speeds beyond the capabilities of conventional computers. For this, we have two main things. We have the graphics processing units, or GPUs. They specialize in processors designed for rendering graphics in computer, and their parallel architecture makes them well suited for general purposes. And at the same time, as I've already mentioned, parallel processing, it basically breaks down complex tasks into smaller tasks, and that can be solved simultaneously. So it doesn't have to just go in a linear serial way, since it can use multiple processors at once. So now we're actually dwelling into data science. And here I divided data sciences in three main aspects. We can look into the machine learning part, which has the predictive analytics, the image and speech recognition, natural language processing, fraud detection, all these things. And then we've also talked about the high performance computation, the hardware, such as the GPUs or the parallel processing. Also some software that it's more what we as users deal with. And finally, the ethical and legal aspects that I would like to stress again, we have to be mindful of, such as the data collection, like privacy concerns, the data analysis, the bias and fairness of the results, the data-driven decision-making. So who is accountable for this? If the machine learning algorithm is using some results or protected authorship content from someone, how is this fair? If we're just going to use it, can it just use it? All these things have to be addressed one way or another. And this also tells us about emerging challenges. Machine learning is very useful. It's a very powerful tool. However, it does come with some challenges and some discussions that need to be taken and considered before fully implementing it everywhere. We're going to go back to the handbook so that we can just remind ourselves of the different algorithms that are out there. I just like to remind everyone that the primary objectives of the handbook is to understand the basics of machine learning, explore various machine learning algorithms, know when to apply the machine learning algorithms to different research scenarios or data processing in general. And finally, hopefully after this, everyone will have an algorithm criterion starting to shape. So you will know a little bit more of what to look for when you think about applying machine learning and what kind of things you expect from it. So now we're going to go to the different algorithms, just go in and see a little bit of the pages that I've made for the handbook. I'm just going to present one algorithm per chapter just to illustrate how it works. I hopefully selected the most relevant ones, so everyone will have a very general overview of what these families of algorithms have to offer. First, we're going to go into supervised learning. I don't know if you remember, but supervised learning is an approach to machine learning where the model has access to labeled data for which the output is known. The goal is to train the model to detect underlying patterns to yield good results with never before seen data. Here, we're going to see a lot of algorithms that are very closely related to previously statistical methods, mainly used in the 60s. And here we have like classification and regression. But for now, I'm going to talk about a very specific kind of classification, which is the bounding boxes. Bounding boxes, the main idea behind it is a binary classification. It's a type of machine learning where the goal is to categorize input data into one of two possible classes or categories. The algorithm aims to learn decision boundary that separates the data points into distinct groups based on features or attributes. Learning a class from examples is based on the positive and negative examples that affect the output. We can take two qualities of classification and find the population in the variables that are within the class. For example, if we have points x acquires a value of 1 or plus, if you want to use negative and positive, and if it's negative, then it acquires a value of 0. So basically, what happens is that you have the A's, you can see maybe here, and the B's, and these are features. We can say like specific sizes, specific colors, specific shapes. And it sets a box, it sets some pattern, some parameter in the x-axis and then in the y-axis, and everything inside this newly formed box is positive and everything outside it, it's negative. And that's how the primary classification is going to be carried out. So the AB values fix the hypothesis. These hypotheses are the things that we believe to be true. These parameters can be changed. The hypothesis always change, and we can try several of them to try to find the best possible classification parameters. In a model, the hypothesis can correctly classify the data. When this happens, we get true positives. and true negatives. The mislabeling of the samples through the algorithm are known as model errors. The accuracy of the model has to be consistently supervised by an expert that constantly examines and interprets the model's results. A hypothesis class is a set of parametric model we choose for our learner. The most specific hypothesis contains all the positives, like all the positive balls. You can see it here. And the most general one excludes all the negative balls, but there's like some room in between. We want to be somewhere in between. The hypothesis type depends on the model, but normally the middle point between most specific and general is taken. The data is then labeled in two ways, as positive and negative, but several boxes can be implemented at the same time. So you get like very specific, very complex classifications if you apply a bunch of them at the same time. Perfect learning is very hard to achieve, if not impossible. The classification does not have to have everything right. Machine learning permits some errors, and it actually works very well with it. When starting a machine learning analysis, we face a group of concepts that we aim to learn. Within the group, there are many hypotheses for the learner to use. The objective is to select the ones, like many of them, many hypotheses, with a small generalization that will allow us to learn specific concept in our data. So now we have the red pages that I like. And here we just have what can we do with bounding boxes? It's object detection task. Bounding boxes are utilized to identify and locate specific objects within an image. How does it do it? The learning process involves training a model to recognize and predict bounding boxes around objects, providing spatial information about their position in the image. The machine learning models is trained to understand the relationship between the visual features in the boxes and the corresponding object classes. The results that we get is a model that can recognize and localize objects in new, unseen images. This model can classify objects and get their precise location, and to understand spatial distribution. The way this is applied mostly is by object detection, image segmentation, and it helps us understand how computers see images, how they process the data in the images, basically how they see the world around us and how they process it. Now we're going to talk a little about Bayesian theory. This is probably one of my favorite families. So here, data in machine learning project typically comes from a process whose details are not fully known. This lack of knowledge is embraced by modeling the process as a random occurrence. Even if the data is generated through a fully deterministic process, because we do not have complete knowledge of all these parts, we model it as a random. Bayesian theory or Bayesian processes or algorithms get their name because they use Bayes' rule. I'm not going to present Bayes' rule, especially because the notation might be a little bit not so friendly, but basically is a principle from probability theory that helped us make better predictions by updating our beliefs based on new evidence. Imagine you want to know how likely something is to be, given some evidence. Bayes' rule helps us combine two things. The first one is the prior knowledge, what we already believe or know about the situation. And the second one is the new evidence, the likelihood of observing this new data if what we believe in the first point is true. Bayes' rule formula has many parts to it. It mainly has four. The prior is our initial belief or assumption about the probability of an event before seeing any new data or evidence. The likelihood tells us how probable the new evidence is, assuming our hypothesis is true. The posterior is our updated belief about the probability of the hypothesis after considering the new evidence. And finally, the evidence is just a term that normalizes the posterior. is the total probability of observing the evidence regardless of which hypothesis it is. So basically, if we start with the prior, which is the pink line here, it's just a shape of some distribution, in this case Gaussian, that is aiming to predict something. Then we apply the likelihood to it. And what the likelihood will do is it will compress it or enlarge it, make it fatter, make it thinner, make it taller, make it shorter. And then we will get a posterior, which is in the shape of the very dark blue line that we can see here. This very large, larger distribution needs to be normalized. So it basically means that so many information has been added to it that it just becomes bigger, like actually bigger in size. So in order to be compared to other priors, posteriors, and all this, we have to normalize it, make it kind of the same size for all of them to be compared. And this is what the evidence does. That's why it's like an independent term in this case. Finally, we get to the red part. So what can we do with Bayes' rule? Bayesian methods are used to update the probability of a hypothesis as more evidence or information becomes available. The learning process involves applying Bayes' rule to combine prior knowledge, prior probability, with new evidence, likelihood, to form a revised belief or posterior. The model continuously updates its predictions as new data becomes available, making it highly adaptable to changes in the data. A model that can refine its prediction over time with new data is what we get from this. And one, we can calculate the probability of outcomes given prior new information. And two, we can adapt dynamically to changes in the environment for the data. The main application for this is things that are actually quite useful. For example, spell filtering. For everyone that has an email, all those annoying emails that we don't want to see in our inbox are filtered out through these kind of processes. It's also used in medical diagnosis and decision-making under uncertainty in fields such as healthcare, finance, and large language models such as ChatGPT. Additionally, I wanted to just add this to this chapter. Gaussian processes is a flexible, non-parametric Bayesian approach to modeling distributions of their functions. It is a way to make predictions about data by modeling a smooth function like a curve that fits your data points. It's commonly used for tasks where you want to predict continuous values. So basically what we have are observations, data points. Here you can see them in very dark blue again. And we want to fit curves that go through those points so that we can do later on predictions on unseen data. These predictions are the solid lines that you can see here. And the Gaussian process, we iterate this many, many times, repeat it over and over and over again. There's this area, which is the confidence interval, which represents the Gaussian process uncertainty in its predictions. So the wider the shade, the less sure it is of the predictions within this region. But as the iteration goes on and on, this area will be thinner and thinner. It's a very good prediction model because it not only gives you a prediction, but it also tells you how uncertain that prediction is. Here in the dotted line, you can see that it's trying to aim at like truth, which is this line here. And if you iterate it enough times and your model is good enough, hopefully you'll get to that line or very close to it. So what can we do with Gaussian process? Object detection. Gaussian processes are used for regression and probabilistic modeling tasks, providing a flexible, non-parametric approach to prediction. The model assumes that the data points follow a multivariate normal distribution. It learns a distribution over functions and predicts by calculating the mean and variance for each point. The model can make smooth, continuous predictions with uncertainty quantification, and it predicts outcomes with confidence intervals, and it adapts to complex non-linear patterns in data. This is same as Gaussian processes used in time series forecasting, spatial data analysis, and optimization tasks. So this is very recurrent. After that, I want to talk about the parametric methods in machine learning, where the model makes assumptions about the form or shape of the data and uses a set number of features to capture patterns. These methods create a simplified version of the data using fixed structure, which doesn't change regardless of how much new data is added. So this is very different from the previous one. This will not change as dynamically as the previous one. These models are efficient because once they are trained, they rely on this fixed structure. And while it might limit their ability to handle complex patterns, it's a very good, efficient method for established patterns that we've already kind of understood throughout this modeling. Here I would like to introduce two concepts. The main one is, the main two are bias, which occurs when a model makes overly simple or incorrect assumptions about the data. High bias means the model is too simplistic and fails to capture the true pattern, resulting in underfitting. And then we also have variance, which occurs when a model is too sensitive to small changes in the data. High variance means the model is too flexible, fitting the noise in the data, which leads to overfitting. Here, I made a little representation of the bias-variance trade-off. So basically, if you have a data set, you want to apply a model to it. And if it's too simple, like a linear regression might not be the best for the kind of data you have, it will have a high bias and a low variance. And this will result in underfitting. If you add a very complex model that basically touches every point of your whole data set, then it's overfitting. These will have a high variance and a low bias. And again, you want a middle point, but the desired model actually has low bias and low variance that will help you with this trade-off and will probably give you the best representation of your data. The parametric regression basically is a method used to predict unknown outcomes called dependent variables based on some input data called independent variables. This regression is parametric because it assumes that the relationship between the input and output follows a known shape or model, which is defined by a set of key values called parameters. Here, to check how good the model is, you can calculate the mean square error, for example. There's many kinds of errors that you can calculate. And the goal of the training the model is to adjust the parameters in a way that it minimizes the error, meaning the model makes smaller and fewer mistakes. Afterwards, the model is ready to predict future values based on new input data. So here's just some illustration of what I just said. You have some kind of model, then you have a specific set of parameters that can be seen in your graph as some angle or some intersection in the y-axis. And if you play with your parameters enough, you might get to very good predictions. So here, what can we do with parametric regression? Parametric regression is used to model the relationship between input features and continuous target variable, assuming a predefined functional form with fixed number of parameters. The model is trained by estimating the parameters that best fit the data, typically by minimizing a loss function like mean square error. Once the parameters are learned, the model can predict outcomes for new data. What we get from it is a model that can efficiently predict outcomes, assuming the data follows the specified functional form. This model can provide fast predictions using a fixed number of parameters, and it's very cheap, computationally speaking. The application is mainly linear regression for example, house price prediction, polynomial regression for growth trends, and logistic regression for binary outcome prediction in finance and healthcare. Now we're going to talk about multidimensional datasets. Here we basically have the datasets that have a lot of information that are usually represented in matrices. Each feature adds a new dimension to the data, which allows for more detailed analysis. Here, I'm just trying to show that even though you might have several examples, each of the rows might be the examples, and each of the columns might be a characteristic of that sample, such as color, shape, size. Here we're going to dwell into a very trendy one, very famous one, which is a neural network. This is a machine learning model inspired by the structure and function of human brain. It consists of layers of interconnected nodes called neurons, which process input data to make predictions or decisions. The idea behind it is that it kind of looks at how our brain works. Neurons here are the basic units of the neural network. Each neuron receives one or more inputs, processes them, and passes the output to the next layer. Here we can see a very quick drawing of a neuron, and under it, we can see a neural network neuron. So basically what happens is that you have a lot of inputs. One of them might have biases, and they also have weights. And then they are processed with some linear function. Inside the neuron, a lot of functions happen until an activation function produces the output, which is just some signal that the next step is to be taken. This reminds us of how humans process data, and it becomes a very complex system. Neural network architecture includes, like the previous one is just one node, but you can add a lot of nodes and they will simultaneously process your data. Mainly, we have to be aware of the layers. The input layer, this is where the network receives the input data. Each feature of the data corresponds to a node. Then the hidden layers, it can be very deep. It have many, many layers. We don't know because this is the part that becomes like a little bit of a black box. These layers perform the actual processing of the input data by applying functions. They capture complex patterns and relationships in the data. And finally, we have the output layer. This layer gives the final prediction, and it gives our final result. Neural networks can be very, very complex, but the main way or the basic way to implement them is through forward propagation. It basically goes forward, you input data, process it, and then you have some kind of output. And then it also goes back. When it goes back, we have the back propagation. Here, the error from the output is propagated backward through the network, and the weights and biases that we used are adjusted to reduce the error. So this happens many times, goes forward and backward, and this is how the optimization of the neural network will take place. Through multiple iterations, also called epochs, the network gradually improves by adjusting different parameters. So what can we do with neural networks? Neural networks are used for a variety of tasks, including classification, regression, pattern recognition, by learning complex patterns in data. They basically do everything, but it's not always the best course of action because they also take a lot of memory, a lot of computational power to introduce. The learning process involves multiple layers of interconnected neurons. There's different kinds of architectures that we have to take into account depending on what you want to do. Talking to an expert might be the best solution if you're not familiar with this. And the result is a model that can learn and model complex nonlinear relationships. This model can handle large, high-dimensional datasets and complex tasks and adapt to various types of data. It's mainly applied to image recognition and natural language processing. Speech recognition and autonomous systems. So it's used pretty much everywhere. Finally, we come to the last part of the presentation. And I would like to invite anyone that wants to discuss more specific handling of their analysis, or if they have any questions about some data that they're handling right now and their plans to incorporate machine learning to it. Maybe after this presentation, they already have some idea of what to do next. So yeah, this is for now it, and I hope everyone got something out of this.